There is only one form of energy that mankind can look to in the long run, and that's solar energy. The amount of light coming from the sun is more than enough to support mankind's energy needs for the next few centuries and beyond. We're working on developing new electronic materials to improve the efficiency of bulk heterojunction solar cells. Materials that can address some of the limitations and improve their quantum efficiencies dramatically. There's a new type of solar cell which uses two different organic polymers, and you mix them together and they make individual domains, as if when you shake up oil and water, right? It never really mixes into a solution. So you end up with a phase boundary throughout the bulk of the material. So the light will be absorbed at the boundary between the two phases, and the electrons will be separated very efficiently. Nanoscience and nanotechnology is really at the core of this whole project. Pitt has this theme that they call essentially nano, built around their nanoscience. Well, the nanoparticles that we use really fit that theme well because their electronic properties are controlled primarily by the physical size of the materials. And so what we're doing is we're taking these nanoparticles and adding them to these bulk heterojunction solar cells in a way that they'll be able to absorb light. We can manipulate the size of the nanoparticle and manipulate the color of the light it absorbs. And so we'll be able to access the entire solar spectrum, or as much of it as we want. What we're focusing on right now in my research is take these materials, put them on electrodes that also have a polymer film, so that we can study the injection of the electron from the nanoparticle into the conducting polymer material. And that's our current challenge. When I first started as a scientist, I had an expertise in a certain area, and over time I've become much more of a generalist. So my student, Angie Wu, for example, has learned how to do the traditional inorganic synthesis to actually make these nanoparticle materials. She's had to work with another student to do the electrochemical work to find out the energetics of these materials. Our group in Israel that we're collaborating with does what's called ultraviolet photoemission spectroscopy, where they do a similar sort of thing, but in an ultra-high vacuum chamber where they flash the sample with light and then measure the energy of the electrons that escape. And so all of these experiments we take together and we put into a physical model, so it's a vast array of different tools that need to be used to solve these problems. We know much about the simple individual steps, but we don't know how to put multiple steps together in a clean and organized way to create more complex materials. That's really what I see as a big new challenge for physical chemistry in the 21st century. The value of basic research can be underscored through a wonderful story or question. Would you have thought to give money to Albert Einstein to do theory on how light gets absorbed and emitted from matter? But his ideas are at the core of the development of the laser, and we know that laser surgery now is the way that many people are saved from going blind. The thing about basic research is you can never really predict what its outcomes will be. Education is a primary part of the mission for any academic scientist. And so that's a big motivator for me as well, watching students evolve from when they first joined the research group. And you know, these are people who've been taking courses for 16 years, right? And they have to learn how to start to be an independent thinker and an independent learner. They have to start to learn how to define their own questions and how to answer those. And that's the key thing I tell every student when he or she comes to join my group. I run a very flexible, free-form group. Students have a lot of freedom because I think that that's essential for them to learn how to be a creative and independent scientist. Hopefully, someday these materials would be like a paint that you could just spray onto the roof of your house. You could put an electrode over the top and have a solar cell that would be very cheaply manufactured and hopefully compete effectively with fossil fuels, which are mankind's dominant form of energy today.